Yeah, this is the last one. So I thought I'd tell you. I mentioned this a few times during the lectures, why max cut is my favorite problem. So today I'll tell you why. Yeah, actually, before we get started, I'm just going to leave this to the end. But while we're here, I may as well mention it. Anil reminded me. One may ask, what is on the final? It's this. Lectures 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 17, etc. up to 24. So I think that's like midterm 1, 2, 3, plus approximation algorithms, plus linear algebra, plus random walks, minus Gödel. That's it. So you can double check that that's correct. But we'll have a post on it in Piazza just to be sure. But I think this is it. Also, yeah, you got to fill this in. It's very easy, the faculty course evaluations. So please do that before May 8th. Any questions?
Did you get the email that Andrew Moore is reading all of the FCEs in great detail?
He's reading all the head of the dean is reading all the FCEs in great detail? Yeah, I hope so. I guess so. Actually, I got a different email that he was reading. Well, no, I guess I didn't get that email. But write something nice, I guess. OK. Let's see. Mention that. Oh, yeah. So, OK, I guess in this lecture, I'm just going to tell you some stories about theoretical computer science. You know, most of the time when I give you the lecture, I want it to be understandable. I hope you understand like every single thing. But today I'll be glossing over some of the details for the sake of the story. So, if you don't follow every detail, that's all right, because I'm skipping some of them. It's going to be tough to eat a cupcake and lecture. OK. So, yeah, these theoretical computer scientists like us are so proud of ourselves because we invented like polynomial time and NP completeness, and we had this like glorious theory about the computational complexity of almost every problem, it seems. And there's a couple of problems that are famous for being not able to be classified, or we don't know exactly their complexity yet. Probably the most famous is factoring, which Anil talked about last time. We kind of believe it's not NP complete, but we also don't know how to do it in polynomial time unless you're allowed a quantum computer. There's also graph isomorphism, which is a very interesting problem. I think most people kind of think you can do it in polynomial time, but we don't know how to do it. But we also don't believe it's NP complete. So that's a couple of problems that seem to elude our classification grasp. But you may sometimes hear the following things said. I quoted this from the Handbook of Algorithms and Theory of Computation. It said that the vast majority of natural problems resolve themselves as either being NP or NP complete. And unless you uncover a specific connection to one of these two above problems, it's more likely offhand that your problem simply needs more work. Which is kind of a rude thing for them to say, quite frankly. It's like, you just didn't try hard enough. Well, that's a common sentiment, I guess, that like pretty much we know everything except for maybe the complexity of these two problems. However, that's totally wrong, Handbook of Algorithms and Theory of Computation. I'm here to tell you that that's totally not true. Actually, there's like a tremendous number of important natural problems that we do not know to be in polynomial time, and we don't know if they're NP hard either. And I'll give you some examples, mainly one example, concerning my favorite problem, max cut. So max cut, I like to think about it as like pretty much the simplest interesting algorithms problem there is. I mean, it almost cannot get simpler. Like you got a graph. You're supposed to label the two vertices with, I don't know, before I used to call it blue and yellow. And you want to have as many edges as you can with two colors. It doesn't get a lot simpler than that. Or another way to say it is you're given a graph. Here I just colored the vertices to indicate them. And what you're really trying to do is split the vertices into two sides, two parts, like the left side and the right side. So let's make a bipartition such that you have as many edges as, you can barely see the bottom. You have as many edges possible going from the left side to the right side. So these are the same graph. I just drew them differently. Like red here is connected to light blue, black, and light green. It's the same thing over here. But you're trying to separate them into two sides so that you get as many edges going across as you can. OK, so here's what I think is a natural problem. It's concerned with approximation algorithms. So we all saw when we talked about NP hardness that max cut, to find the maximum cut, the best partition, is NP hard. But in light of that, we tried to do some approximation algorithms. And you might just ask, what about finding a partition into two parts that gets like 90% of whatever the optimum is? That's a nice problem. If you could like write some code in random polynomial time, you could prove that it always got at least 90% of the optimum. That'd be pretty good, right? Well, here's an example of a problem that we do not know how to do in polynomial time. And we do not know if it's NP-hard. So I don't know. To me, it doesn't get that much more natural than this. I mean, it's the simplest possible problem, I think, max cut. It's a nice guarantee. Just try to get 90% of the optimum. We have no clue the computational complexity of this. Maybe you can do it in linear time. Maybe it requires exponential time. Yeah, we don't know. So it's like factoring in that sense, or graph isomorphism. Actually, it's worse, because those problems, we kind of know something about their complexity. Like, for example, we're pretty sure they're not NP-hard, but here we have no idea. It's a similar situation, actually, for many approximation algorithms problems. If you remember way back, you probably don't remember, but in lecture 15, I told you a similar thing about the vertex cover problem, and whether or not you could get an approximation algorithm for it that guaranteed approximation factor better than 2, twice the optimum. But I won't tell you about all these other problems. I'll tell you about max cut because it's my favorite one. OK, so I selected this number 90% kind of carefully. We know that actually, for the maximum cut problem, you can achieve 50% of the optimum in polynomial time. Actually, we did this in 2 different lectures. One was in the first graph theory lecture. We showed a local search algorithm that achieves it. And then in the probability lecture, we showed a randomized algorithm. Actually, just pick a random bipartition that also achieves it. So that's good. And it was the best. This is the best known fact for like 20 years. But actually, impressively, 20 years later, they found a better algorithm for maximum cuts. And I'll tell it to you. Actually, it's a bit tricky, so I cannot explain all of it. This is a bit where we're getting into the parts where I'm going to gloss over some details. But it's a nice algorithm, so I wanted to tell you about it. OK, so you're given a graph, and you want to split the vertices into like left side and right side so that whenever you have an edge, hopefully one of its endpoints is on the left and one of its endpoints is on the right. OK, and I'm going to call left -1 and right +1. OK, and I'm going to just imagine the number line, and like here's -1, here's +1. And I can think of the problem as I want to take these, I think there's 10 here, colored dots and put them on -1 or +1 so that hopefully as many edges as possible are going from -1 to +1. And I'll just start with any partition, maybe, let's say, just like in the local search algorithm. And instead of actually points, I drew them as vectors here. But like I have one vector for each vertex. Like the red vertex is represented by this red vector. And in my arbitrary partition, I put it on the left, -1 to start. The pink one I put on the right arbitrarily to start. And this is some bipartition. And some of the edges, like the one between, I don't know, red and black, they both got assigned -1. So it's not cut. So I'm not happy about that. But between red and light green, they got assigned different sides. So I'm happy about that. OK, so now I'm going to imagine trying to like improve this partition to get more edges cut. And that's actually exactly how that local search algorithm worked. It just went through all the vertices one by one. It's like, OK, what about red? And it thinks to itself, OK, right now red is connected to black, light blue, and light green. 2 of those guys are already on the left, and 1 is on the right. So actually, it would be better if red was on the right. So then it's like, all right, I'll just flip it so that it's pointing to the right. OK, and local search algorithm just keeps going through all the vertices, checking to see if it would be better if they were on the other side. And it keeps doing that until it gets to a situation where it can't improve the partition anymore, and then it's done. And that got 50% of the optimum. But we're going to do a better algorithm. And somehow, maybe some of the intuition is that like this move that we just did to flip the red guy from this side to that side was too drastic. Like, it wasn't a bad idea. It improved the number of edges you cut, but it wasn't necessarily like definitely the greatest move ever because we also had an edge cut between red and green that we just screwed up when we moved red to the other side. So it'd be cool maybe if we could somehow like partly flip it or something. So yeah, so we're just going to imagine we're going to do that. And we're going to do that just by like moving red only half the way. And we're going to go into the second dimension. So yeah, I mean, you cannot see it because it's misaligned. But this says R2. And Now we're just going to imagine that these vectors are all sitting in 2 dimensions. And we're going to say, let's move red like some of the way to the other side. And like this is really, it's like pointing like down in the plane. So, OK, maybe now it's not exactly clear like what I'm saying or where I'm going with this, but I'll try to explain. Now we're going to like look at another vertex like this light blue one over here. And we're going to look at who it's connected to, red and dark green and pink. And we're going to look at where the red and dark green and pink vectors are. Here they are. And this blue guy wants to be far away from them. He wants to, these edges you're trying to cut. So you want to imagine this blue vector is far away from them. So just imagine like it's kind of, as I said before, I don't know anything about physics or anything, but imagine it's sort of like repelled by the vectors for the vertices that light blue is attached to, which is red, green, and pink. So like somehow imagine that like it tries to move far away from them. And it can even go into like another dimension if it wants. So here, I couldn't draw it, but like imagine it's like coming out of the screen or something, and it's in 3 dimensions. And somehow this algorithm is going to keep going, letting these vectors repel. And 2 vectors are going to repel if they are associated to vertices that have an edge between them, because these are ones that you want to have far apart somehow. So it's not exactly clear what it means, but imagine these are like physical objects, and they have like whatever magnets or electricity or something or springs, and they're trying to all get far apart from each other, and you allow them to go into higher dimensions if they want to. And eventually, like it'll become like stable, and you'll have a configuration of these vectors in maybe some higher number of dimensions, n. Again, each vertex is going to be represented by a vector, and they're trying to be far apart from the vectors that they have an edge to in the graph. Does that make some sense? And this is the most technical thing in all the slides, but like, you can imagine that the end goal of this process of letting all these vectors repel is to have a vector, sigma sub v, a unit vector for each vertex in the graph. You're going to want to try to maximize this thing, which is kind of unreadable. But what in particular you should look at is this quantity right here is the dot product of 2 vectors. So you're going to look at vectors that are connected by an edge, that correspond to vertices connected by an edge. And this is their dot product. So this is the dot product of 2 unit vectors. If these 2 unit vectors are exactly opposite, they're like anti-parallel, then that dot product is going to be -1. And then you'll get a half minus a half times -1, which is 1. So it's kind of like you get like 1 point if you have an edge connecting 2 vectors that are anti-parallel. And on the other hand, if they point in the same direction, like they're the same vector, their dot product will be 1. This is a half minus a half times 1 will be 0. It's kind of like you got 0 points if you took 2 vectors that had an edge between them in the graph and put them on top of each other. So it's kind of similar to like what you're trying to do in the max cut problem. Like you're trying to look at all the edges, put them somewhere, put the vertices somewhere so that the edges are far apart. Here you're kind of putting them on the surface of a sphere, and you get like 1 point if you put them totally opposite to each other, 0 points if they're on top of each other, like half a point if they're orthogonal, something like that. So this is some kind of optimization problem to find the best vectors to maximize this. This is the sum over all edges. And it looks like even crazier. Like, OK, max cut, I could explain it to you briefly. This looks kind of complicated. But the amazing thing is you can actually, there's a polynomial time algorithm that finds those optimal vectors, like the best vectors for maximizing this. It's not quite the same as like what I told you about like just starting the vectors out and somehow like maybe imagining a physical system that let them repel each other. But it's not completely different from that either. And it looks kind of amazing because you're doing a maximization over all vectors in space. I mean, that sounds crazy, but this is an amazingly awesome fact. How you actually do it is a long and very interesting story, which I do not have time to tell. It starts with this, like my favorite algorithm in the whole world, which is linear programming. I don't know, I'm a bit sad we never got a chance to talk about it in this class, but hopefully you'll learn about it in your career. Linear programming itself has a very cool story. For example, before we were all born, the New York Times had a headline on its front page saying, "A Soviet discovery rocks the world of mathematics." Like A1, and that was all about the fact that somebody showed that this linear programming thing can be done in polynomial time. Anyway, that's a component of this algorithm for finding the vectors. The last component is a bunch of linear algebra. And these were the heroes that like did all this stuff. But long story short, it turns out you can find these optimum vectors by this vector kind of repelling thing. So what's the point? I mean, we're not done, right? We're trying to actually get an algorithm for max cut. We're trying to split the two vertices into two sides so that hopefully lots of edges are going between the left side and the right side. And for some reason, we just found these vectors that are kind of doing a similar thing. Like they're far apart on average whenever you have two vectors connected by an edge. But still, we have to find a cut. We have to partition them into two sides. Can anybody suggest what the last step of the algorithm is going to be? How you can get like a partition of the vertices that are hopefully cuts the edges? Yeah? Yeah, that's close. So the suggestion there was something like, let's say, look at the first coordinate of the vector. If it's positive, put it on one side. If it's negative, put it on the other side. Another way to say that would be like, look at the first coordinate axis, which may be up in this picture, and like everything above that axis, put it on one side. Everything below that axis, put it on the other side. That's a good idea. There's one like twist you can add to that idea to make it a little bit better. Maybe back there? Oh, well, all right, yeah. Yeah, what were you going to say? Yeah, these are all the same ideas. So what you could do is either you could like first like randomly rotate the sphere, like, and then take your idea, like take everything above the top. Or equivalently, you can like pick a random plane through the origin, like maybe this. And it's actually in this algorithm, it's important to do it randomly and put all the vertices above the plane on one side and all the vertices below the plane on the other side. So here, like red, purple, pink, and green went to one side. The rest went to the other side. And it turns out that on average, that gives like a pretty good partition. Kind of makes sense, because this whole vector thing was designed so that like, I don't know if there's a good example here, like gold and dark green had an edge between them. And indeed, like this vector repelling thing put them far apart. So you can analyze this. And actually, it's not that hard. It takes a little geometry. I was almost going to do it, but then I decided, it's the last day. Like, let's skip the math. But it's not that hard. And it turns out you can prove that this overall algorithm, first find these vectors, then put in this random hyperplane to split them. In expectation, the number of edges it cuts is at least 87.8% of the maximum, which is pretty good. It's a lot better than the 50% we got before. Actually, it's not. Oh, this is due to Gomez and Williamson from 1994. And it's actually not just 87.8%. It's this number, 87.856720, et cetera, percent, which is a pretty crazy looking number. Turns out to be, first you take the solution of this equation, tan theta over 2 equals theta, plug it into 2 over pi sine theta. That's the answer. That's pretty crazy. Who's counting, though? So that was a pretty cool algorithm, and it got a great result for max cut. It's actually used in practice for max cut. I mean, this literally is used in practice to find good partitions of graphs. And it's guaranteed to get like at least 87.8% of the optimum. But I chose this number 90% kind of carefully. Could we do any better is the question. All right, so as of 1994, we know that you can get 87.8%. That's the algorithm side. And in theoretical computer science, there's always a bit of a divide between the people that work on algorithms and the people that work on like complexity, like the optimists and like the pessimists, the people that are trying to show things are easy, the people trying to show things are hard. So I'm always on the pessimism side, personally. So what can we say about how hard this problem is? OK, so let's turn our attention to the other side, NP hardness results. So back when they invented NP hardness, like the very beginning of the 70s, like one of the first things they proved was that like max cut, in the sense of finding the maximum best cut, finding 100% of the optimum, is NP-hard. That was done by Karp in 1972. But like these days, it's like a homework style problem. Yeah, I can't remember if we explicitly did this exact one, but you could do it. Or you should remind yourself how to do it with the final coming up. Now, nothing happened. Flash forward for like 20 years, and there was a very, very famous theorem proved that Anil mentioned a few lectures ago called the PCP theorem. It's a well-chosen acronym. And it was, PCP stands for probabilistically checkable proofs. It's like an amazing story. It came out of people thinking about cryptography, zero-knowledge proof, interactive proofs. What does it mean to prove things? What does it mean to prove things in a way that doesn't reveal any information about the proof? They were thinking all about these things involving proof. But it turned out, and Anil also mentioned this, that like kind of very amazingly, it also had something to do with NP hardness for approximation algorithms. And in particular, as soon as you prove this PCP theorem, you get that it's hard to, NP hard to find an out, like for an algorithm, it's NP hard for it to find a bipartition in max cut that's at least 99.9999999% of the optimum. I don't know if I got the right number of nines in there. It's very small. It's very close to 1. And you might say, like, this doesn't look that impressive, but it is kind of interesting because, as I mentioned back in the approximation algorithms lecture, there are some NP-hard problems like knapsack, if you ever heard of that, or like traveling salesperson in 2 dimensions, where even though it's NP-hard to find the optimal solution, like the best traveling salesperson tour, in polynomial time you can find like solutions that are like arbitrarily close to optimum. So in some sense, they're like these problems, even though they're NP-hard, they're not really that hard because you can get kind of almost like arbitrarily good solutions to them efficiently. And this theorem kind of shows that's not true for max cut. There's like some barrier below 100% that you can't even reach that barrier. So it's more a theoretical result than a practical one, but that was the story. Now, you might ask, what do these probabilistically checkable proofs have to do with approximation algorithms? So, it's also a long and very interesting story, which I cannot explain to you today, but it's cool. It's a cool connection. OK, so now this part of the lecture, I'm really going to start getting flaky with the details. But I want to tell you about people's ideas to try to improve this result, to show that like max cut is like even harder. So these probabilistically checkable proofs, in some weird way that's hard for me to explain, they can be thought of as like a game involving provers. In fact, you can think of it as like a game involving 2 provers. Like remember in like the interactive proofs, there were like the provers who were like the wizard, and then there was like you who was like the verifier trying to check proofs. Somehow these PCPs involve like you interacting with like 2 provers who are like trying to convince you of something. And so they're like cooperating. They're playing some kind of like max cut-like game. This is like an artistic impression of what is really going on. And you can think of this PCP theorem as showing that like you can make one of these games where the provers, the players, can win at most like 99.9999% of the time. OK. So people were like, that 99.99999 is kind of a joke. Like maybe we can make it smaller and show like a really powerful result. So they wanted to kind of like make this game harder for the players. And I depicted the game here as chess because like if you have chess and you want to like make it like harder for these like top-notch players, one thing you could do is like have them play like a simultaneous chess. So there's something in complexity theory called parallel repetition. It's like a way to make a game harder. And like it's basically you like make them play like many, many copies of the same game at the same time. This is the best thing I can say about it. Yeah? No, it's kind of like, you like ask them like, again, a little bit of an artistic impression, but it's like, you ask them about like, you can imagine like different moves. Like they have like 10 chessboards in front of them, and you're like, they're in different configurations, and you're like, tell me all the best moves that you'd make in all 10 of these positions simultaneously. Something like that. Yeah?
So when you do parallel repetition, you need like both players decide on a move, but they do not see each other's moves after, and then the game changes after they decide their moves.
Yeah, it's something like that. It's a little hard for me. getting into trouble to try to explain it. Actually, it's a bit more like, yeah. The thing that it's really like is like, actually, like imagine like, okay, imagine you're like the police, right? This is a bit of a digression, but like, and like this crime is committed and you picked up like 2 suspects and you think like one of them did it. So you got to interrogate them, right? But what do you always do if you're the police? Well, I've never been the police, but in movies, what they do, right, is they put them into like separate rooms and they like interrogate them separately and kind of like cross-check the answers, right? And that's tricky for the suspects because they don't know whether or not they should lie about it, because like if they lie about something that might help them get off, but then like the police are going to cross-check it with the other person. And like that's kind of what's going on here. Like you kind of like ask, you know, Kasparov, like, okay, what's the best? You think like you're going to win the situation. Like, what's the best move here? And you know, maybe he is going to win, and he can just tell the truth about what the best move is. But maybe he's lost, so he has to kind of trick you into thinking that like there's a good move. But then you also ask Carlson the same thing, and like he has to also guess like what Kasparov is saying to like confirm this is the best move. So that's just an additional artistic impression of what's going on. But somehow it gets harder and harder if like they have to do this about like many separate games of chess simultaneously. I don't know if that really answered your question, but it's some picture of what happens in the game. Any other questions, though? It's an interesting topic. OK, so there's this theoretical computer scientist, not a chess player, Ron Raz, who actually proved a famous theorem saying that this actually does make the game a lot harder, you know, forcing the players to, you know, explain many moves at the same time. But the downside is, like, now it's a very weird game. Like, it used to be just chess, and now it's like, you know, chess played in parallel like many, many times. But anyway, he proved the theorem that's like this. And this theorem, I mean, it's stated in like a unclear way, but it's really a theorem of the form, the following problem is NP hard. And like, how did he prove it? Like a really long reduction from SAT. That's like, you know, trickier than the ones that you'll do in this class. But, you know, he proved some really long reduction from SAT, showing that like something like not only is finding the best move in this like weird parallel chess game like NP hard, but like it's even hard to find a move that's like 1% optimal or like 0.01% optimal. So in some sense, he got that like 99.999 down like really low. So it's like super duper hard, albeit it's for this like really weird problem. OK, but that was awesome because, you know, when we're proving things are NP hard, we have this whole like web where like sometimes it's better to reduce from independent SAT, or it's better to reduce from 3 SAT, or what have you. And like this turned out to be a great problem to reduce from. And so some other smart person, this guy, Hostad, came up with a really cool NP hardness reduction from this fact to a fact about our old friend MaxCut. And he managed to show a reduction which implies that for MaxCut, getting 94.1% of the optimum is NP hard. So not only can you not find the maximum cut, you can't find 95% of the maximum cut, even 94.1%, or apparently it's 16 over 17, a slightly less crazy number. Even that is NP hard. You cannot do that efficiently, assuming P does not equal NP. And this NP hardness reduction is kind of also long and complicated. It involves this topic called Fourier analysis of Boolean functions. I only bring it up because like that's my favorite thing in the whole world. Like that's my favorite topic of all. I mean, how awesome is it? It's like Fourier analysis, but Boolean functions. You see, that's awesome, right? It's no sines and cosines or whatever. It's just good old zeros and ones. Yeah, so I love that stuff, but we will not talk about it. But it's a cool tool in theoretical computer science. OK, so that happened in 1997, and I guess right around when you guys were born. And so this is the state of the world about our knowledge of the computational complexity of MaxCut, the world's simplest algorithms problem, in 1997. So this line indicates approximation factors. So in 72, they showed it's hard to find 100% best optimum MaxCut. And also in the early 70s, they showed that you can get up to half of the maximum cut in polynomial time. And then they proved the PCP theorem and worked super hard and got this down to 0.99999999. And then they got this cool geometric algorithm with the vectors on the sphere and the random hyperplane that got an algorithm that was much better. It got this 0.878 factor. And then they had this long, the parallel, the chess, and the Fourier analysis. And they got the hardness factor down to 0.941, 16 over 17. Now, both of these are kind of crazy numbers, right? So, I mean, people thought this looked pretty unnatural. It's kind of a mystery what the truth was. But, you know, at the very beginning, I mentioned this like cleverly chosen number, 90%, that's between these two numbers. And, you know, it's not covered by either of these results. So it's a problem that we don't know how to solve it in polynomial time. We don't know if it's NP-hard. OK, so that was the situation back when you were born. And it remains the situation to this day, 18 years later. This is all we know. And yeah, this is part of why I like the problem so much. Like, you might find this a little bit boring, but to me, this is like the awesomest and like most simultaneously terrible situation of all time. Like, it keeps me awake at night because, you know, max cut is like the simplest possible algorithms problem. Really, it's just like you got a graph, split it into two sides, the end. And like, you know, these theoretical computer scientists, we're so proud of ourselves. We invented P. We understand computational complexity, and so forth and so on. And like, we can't even understand this one problem. Like, we're still, you know, have this gap in our knowledge. And you know, it could be that you can do it in linear time. Could be that it requires 2 to the omega n time. That's a big gap. We don't know. And you know, you also might say like, well, the 0.878, the 0.941, like these are all kind of weird numbers. But like, to me personally, like it reminds me of like, you know, in physics, they're always obsessing about something like there's something called the fine structure constant. I don't know what it is, but like anytime you read like a popular book about physics, they're like, oh, this 1 over 137, it's like the greatest constant in the universe, and we know it to this many decimal places, and it's so fundamental. But like, I don't know, to me, this is like more fundamental. I don't know anything about physics or electrons or quantum or whatever you need to understand this fine structure constant. But like max cut, man, like it's just a graph and like 2 vertices, like separate the vertices into 2 sides. You know, we don't even know the answer, like the correct answer to like 1 decimal place. So I don't know. I think of this as a very like frustrating and also interesting and exciting question. And you know, it's not just max cut. I mean, if it was just max cut, you know, maybe like, OK, whatever, it's like another one more weird problem like factoring and graph isomorphism. But it's actually the same situation for many, many, many interesting problems. Like, if you remember in lecture 15, I ended with this slide, which is pretty much the exact same picture. For vertex cover, there's this totally trivial polynomial time algorithm that is guaranteed to find you a vertex cover at most 2 times the smallest. And like my favorite paper in the world by Denur and Safra shows that it's hard to find a vertex cover that's at most 1.36 times the smallest. And everywhere in between, it's like another problem that we don't know if it's in P. We don't know if it requires exponential time. Nothing. So there are many problems like this. Like another one is if I give you a 3-colorable graph, can you color it with 1,000 colors in polynomial time? Yeah, we don't know. We don't know anything about that. Yeah. So that's the situation for my favorite problem, though, max cut. And as I said, that's where it stands, you know, to this day in the last 18 years. But some interesting things did happen regarding this problem in the last 18 years. So I want to tell you the story of those things, even though this gap still persists. OK, there's this guy called Subhash Kote. He's a cool dude at NYU. And as the story goes, like he was a grad student. And he was like visiting his relatives back in India. And he's like lying down on the couch. And like he had a very, like, to him, insightful idea, which was this. He's like, you know, this weird parallel chess is like so complicated. Like he's really an expert in like doing these NP hardness reductions. And he's like, wouldn't it be so cool if like you had the same kind of result, but like the game was a lot simpler? Like the chess is too complicated. It'd be cool if the game had this property. And again, this is pretty vague, but like where every move for one player, there was like a unique best move for the other player and vice versa. Like somehow that would be simpler. Like he knew a lot about these NP hardness reductions, and he knew this would make his life easier if such a simpler game were equally hard. He's like, I call this the unique games conjecture. And this turned out to be a very interesting and influential conjecture. Actually, you know, just not too many months ago, 6 months ago, he was in Korea, like shaking the hand of the president of Korea for winning the Neven-Linna Prize, basically for making this conjecture. Neven-Linna Prize is like the top prize in theoretical computer science. So he invented this thing called the unique games conjecture. And it's like a very interesting topic. Like if you're ever in like a gathering, like a party, and it's like all theoretical computer scientists, and like you want to keep the conversation going, just be like, what do you think about the unique games conjecture? And then they'll just talk to you for hours about it. It's very, very notorious. And actually, what's cool is I can exactly tell you what it is. Like the weird parallel chess, it's like impossible for me to explain. But this, I can tell it to you right now. You can think about it right now. It's like this. This is not how he posed it. I mean, if you read his paper, it's kind of confusing, but turns out it's equivalent to this. It's equivalent to an algorithms problem that I call, I'm the only one in the world, but I call it topography problem. And here's the topography problem. The input is a graph that looks like this. It's a directed graph, and every edge has an integer written on it. OK, that's the input. Directed graph, every edge has an integer on it. And you can kind of think of these like the nodes as cities, and maybe the edges are like elevation differences in meters or something. Tens of meters, I don't know. But you should not necessarily think that it corresponds to a real possible possibility. Like maybe it's impossible for this to be satisfied. But well, I'll give you an example just now. Your task is to label the cities by elevations, by numbers, so that as many of these differences are correct as possible. So let me illustrate it here. Like maybe this is the input. I'm going to give you a possible solution. Maybe you're just like, OK, whatever. I'll call this elevation 0. Doesn't really matter. So then it would be logical to call this one plus 2, because then you got this difference correct. It would be logical to call this one minus 1, because then you got this difference correct. It would make sense to call this plus 6, because then you got this difference correct. Now here you got an error. Like not an error, but like you didn't get this edge correct. Because if this is 0 and this is supposed to be minus 3, then this should be minus 3. But like you called it plus 6. Now actually, you can see that it's like inevitable. Like everything was forced, right? There's no way you could have done it differently. So there's no way to actually consistently give elevations to these 4 vertices that all the edges are correct. But your task is just do the best you can. OK, so you may as well call this one plus 2. And in this solution, you got 4 out of the 5 edges right. And that's the best you can do in this particular input. OK, that's the whole problem. Any questions about it? Yeah?
How is this like a game?
No, it's not quite like a game. I mean, the shortest thing I can say is like you can imagine a situation where this graph is always bipartite. And like one player has to like label the elevations of the vertices on the right without knowing the guy on the left is doing, and vice versa. That's the best thing I can say. Yeah, so this is exactly the unique games conjecture. Suppose I give you an input, and I promise you the best solution gets 99.99% of the edges correct. Like maybe I took like a totally valid solution, and I just arbitrarily changed like 0.1% of the edge labels. Your task is to find labels for the vertices that get 1% or 0.01% of the edges correct. So there is a solution out there that gets like practically all the edges correct. You just have to find one that gets like a tiny fraction of the edges correct. The conjecture is that that's NP-hard. And when you hear it like that, actually, it kind of sounds ridiculous. I mean, this problem does not look that hard. And if there's a solution where you get like almost all the edges correct, like how could it be so hard to find a solution where you get like 1% of the edges correct? So you might think it's a very bold conjecture of Subhash Koth to claim that this problem is NP-hard. But he didn't just pull out of the blue. It's actually extremely similar in a way to this weird parallel chess, which we know has this NP-hardness property. It's just like kind of a simplification of it. And actually, when you phrase it like this, it looks real simple, but we don't know. So actually, this is another example of a problem where we don't know if it's in polynomial time, and we don't know if it's NP-hard. So if you want to show it's in polynomial time and disprove this conjecture, well, you can try it. I mean, there's the problem. Just see what you can do. OK. So he invented this problem, Koth, with the idea, because he was like an expert on this picture, that like maybe this would be a nicer problem to reduce from. Because when you're doing these NP-hardness results, right, sometimes it makes a difference where you start. Like it's easier to like show something is NP-hard if you start from Hamiltonian cycle than if you start from vertex cover or whatever. So he's like, maybe we could plug in this topography thing up here and find a better hardness result for max cut. And turns out that worked. So it turns out you can show another reduction that involves lots of Fourier analysis from this problem to doing better than 87.8% for max cut, which, if you recall, is at that exact magic number which the algorithm with the vectors on the sphere and so forth achieves. And it's kind of a seeming miracle that this is exactly the same number. So it actually shows that if you believe this conjecture, we can resolve everything. Like everything matches, and this is the exact, this crazy number with the tans and the sines and whatever is like the exact barrier for like the computational complexity of this simple max cut problem on graphs. So that's proved by these 5 gentlemen. And I'll show you this picture again just to emphasize the point that it exactly matches the algorithm, this NP hardness result. But I want to tell you a little bit about something involved in the NP hardness reduction in this previous slide. So it turns out in this NP hardness reduction, you write down the reduction. It's like an algorithm that transforms like this topography. Wait a minute. It's a reduction from topography to max cut. So it's got to take like a topography instance and transform it into a max cut instance. And you write that down, but then you need to analyze it, right? You need to prove these 2 things, that if this one is a yes instance and this one is a yes instance, and if it's no, it's a no. And proving that required proving a new theorem called Majoritius Stabilis theorem. The exact thing it needed was this theorem. And I'll tell you what this theorem is. So this is going to sound like a total digression, but it's interesting. So imagine you have an election like where there's 2 parties. I guess there's an election coming up in the UK, but there's like 5 parties there. But imagine it's like the US, there's basically 2 parties. And each vote has like a small probability epsilon being miscounted. Like somebody votes, but then like when they read that vote, maybe the voting machine is faulty, or like there's the hanging chads or whatever. And there's like some small chance that a person's vote is misrecorded. Okay? And this could change the outcome of the election, right? It could be that like if you counted all the votes perfectly, like one person would win, one party would win. But because of this, epsilon fraction of the votes got miscounted, like the other party wins. That could happen. And you might try to analyze what's the probability that happens. And it depends a lot on what the voting scheme is. You see, when you have elections, there are many different voting rules that are used in practice. The simplest one is like majority. Whichever party gets the most votes wins. For some odd reason, like almost no country uses that as their voting rule. Like I think Mexico kind of uses it as their voting rule. But like practically every other country doesn't use that, which is sort of weird. In particular, like the US does not use that, right? The US has this like weird electoral college scheme where like you take like majority winner in all the states, but then the states have different weights, and you take some other weighted majority. Okay? And what scheme you use for electing the winner affects like the chance that miscounted votes kind of influence the outcome of the election. And in fact, this really happened if you go into American history in like 2000. There's this election where like some votes were like probably miscounted. And at the global, at the national scale, it wouldn't have mattered, right? But because of the Electoral College, like it all came down to what happened in Florida. So, this voting scheme can really make a difference. And you might try to analyze what voting rule is least susceptible to this problem. And it's a theorem that was proved that basically among all the fair voting schemes, that's a technical term, the one that's least susceptible to miscounts is majority, which sounds very nice. It's actually a pretty hard theorem to prove, but they proved it. And bizarrely, you might say, why am I telling you this story? Like this theorem about voting is literally exactly the theorem you need to like show that this NP hardness reduction is correct about max cut. And you might say, like, that's super weird. Like, what does voting have to do with like NP hardness reductions? Well, it's a long and interesting story, but I do not have time for it today. But it turns out that it does. So if you're into max cut, then you can also get into This theorem is from an area called mathematical social choice, the study of mathematical properties of voting schemes. Okay, so that's kind of interesting. Anyway, overall, this shows this fact that like we now have the perfect understanding of how hard this max cut problem is. To get up to this whatever trigonometric number is, 87.8%, you can do it in polynomial time. And doing better than that is NP hard. The picture is complete if you believe this unique games conjecture that this guy came up with. So, okay, naturally people are like, well, what about this unique games conjecture? So if you believe it, it's actually subsequently turned out that not only do you get the perfect understanding of the complexity of max cut, you also get a perfect understanding of the complexity of vertex cover. Turns out that that super simple approximation algorithm that achieves a factor of 2 is optimal for polynomial time algorithms. And in fact, this cool guy, Raghavendra, in 2009 showed that if you believe the unique games conjecture, you basically resolve the complexity of all constraint satisfaction problems, which is a huge class of algorithms problems. So like that's pretty awesome. Somehow, but like everything is like perfectly understood if you believe this conjecture. The only trouble is that many people disbelieve this conjecture. I mean, at first people are like, yeah, it seems plausible, but then people worked on it. That topography problem I mentioned doesn't seem that hard. They started inventing some sophisticated ideas for trying to solve it. They didn't solve it, but it made them think that maybe this conjecture is not true. And in fact, it's kind of cool because I would say like maybe 50% of the people in the field like think it's true and they're trying to prove it, and 50% of the people think it's not true and they're trying to disprove it. So it's pretty cool. Like in my head, it's like this great battle between like one side of the
Yeah, so this showing you get this all shed any light or shed any insights on all constraint satisfaction problems?
Probably. We don't know for sure. Like we know some great consequences of like if it's true, then we know everything about the hardness of these problems. If it's false, well, what does it mean if it's false? Basically, to show that it's not NP hard, you would show that there's a polynomial time algorithm for it. And basically, we know some theorems that say like this enormous class of polynomial time algorithms based on our most sophisticated techniques do not work. So if you showed it's false, you'd basically have to invent like a super awesome new algorithm that nobody's ever thought of before. So we don't know for sure that it would be awesome for anything else, but we're like pretty convinced like such a glorious algorithm would have to be like super important and powerful. Yeah, so I think it was like a battle between like the people that are trying to prove it and the people that are trying to disprove it. Maybe it was a bit dramatic. It's probably more like this, but sometimes I even think of it in my head as like a race. Like the first team to like prove it or disprove it like wins, but like it's either true or false. So like it's decided who will eventually win, but sometimes I feel like whoever's fastest or best at proving will like make the answer the way they want it to be. Anyway. And also because of this fact that like, there's a lot of disagreement and people are trying to prove it both ways, I actually personally kind of think it's more interesting than P versus NP. P versus NP is like the most famous problem, but except for some like weirdos, pretty much everybody agrees that P does not equal NP, right? We pretty much know the answer. 99.9999999% of people believe that P does not equal NP. But this one, like we really don't know. Like it's like a mystery, Like, yeah. So it's a great mystery to me. That's why I like it very much. Okay, so let me tell you a last story that's about unique games conjecture. And it's about the time that me, Guy Kindler, this guy, my buddy Guy, and this super smart guy, Uri Feiga, we tried to prove it. So the year was like 2005, 2006. We were all working at Microsoft Research up in Seattle, doing our theoretical computer science. And we were like, let's try to prove it. And we had like a cool plan. We had like what we thought was like a really cool plan. It's a kind of a new idea, sort of a twist on this parallel repetition thing. Like this is going to be a good plan. Hopefully we can prove the theorem. And it's kind of very interesting to us because something really weird happened. Like, we worked out how our plan might work, and like everything boiled down to a question about foam. And that's not like a technical term. That's really like the thing with the bubbles, like foam. Like it all boiled down to a question about foam, which I'll now try to explain this question to you. You might ask, what does that have to do with parallel repetition? It's a very long and interesting story. So what was this question that our whole plan boiled down to? I'll state it here. You could call it the cubical foam problem. It's actually another way to say it. It's kind of about like tiling space. Like, you know those like M.C. Escher like pictures where like you have the fish or whatever, and like you shift it all around and it exactly tiles space? Same kind of question. So like, what I'm looking for in this problem is a shape. Let's imagine it's 3 dimensions, like a shape with the following property. If you like shift it around by like all integer amounts, like up, right, down, left, whatever, by like an integer amount, it should exactly cover up space. Okay? That's not too hard to do. Like, you can take a cube, it'll have that property. But what you're trying to do is find such a shape whose surface area is as small as possible. And the reason I relate it to foam, or it's sometimes thought of as a foam problem, is bubbles have this property that, due to physics or something, they want to have the smallest possible surface area, which is why if you just have like one bubble, it's a sphere, because that's the shape with the enclosing a fixed amount of air with the smallest surface area, sphere. But then there are all these interesting mathematical questions. If you like put them together in foams and they have to kind of fill out space, what shape will they take? They're always trying to minimize their surface area, but they got to, if they come together as foam, fill up space. And this is the question that turned out to be relevant for us. So let me draw you the problem in 2 dimensions where it's not too hard. So this is 2-dimensional space. And as I said, a square works. A square is a shape that it has perimeter 4. And if you like shift it around like down, left, left, if you just shift it around by the integers, it exactly covers up space. This is like a foam made of like square bubbles, but it's in 2 dimensions. So who can say what's going on there? Great. So this is an example of an acceptable shape, and we're trying to look at like the size of its surface or its perimeter, and this square has perimeter 4. Turns out there's another shape that works in 2 dimensions that has a smaller perimeter. Can anybody guess what the shape might look like? If you actually need to, okay, it's not quite the same thing, but if you need to fill up like 2-dimensional space with like a tiling copy of like one shape and you want to have small perimeter, do you know what like honeybees do? Yeah, they use a hexagon. So this is a carefully chosen hexagon. It's got perimeter √6 plus √2, which is 3.84, which is a bit smaller than 4. And it's carefully chosen because if you look, you like shift it down, left, etc. It exactly, you can do this indefinitely. It'll cover up the whole sheet of paper. And actually, we saw 2 examples, this square with perimeter 4, and this hexagon with perimeter 3.84. And actually, this hexagon is the best solution in 2 dimensions. You can try to prove that too. It's not super hard. You can try to prove it. OK, what about 3 dimensions? That's a little bit trickier. So 3 dimensions is a little trickier. And one thing you can do to get some kind of answer is you can say, well, I had a solution in 2 dimensions, these squares. Let me flatten it out and then like extrude it up and like connect it by a prism and get a cube. And then this would work. Like I could take this cube and shift it around. If you kind of shift it around horizontally, it'll cover up space. And then you can just like layer it by shifting it up and down as well. So a cube will cover up space by integer translations. And its surface area is, the unit cube has surface area 6, because it has 6 faces, each of which is a unit square. OK, and that works. So 6. Now, if you're smarter, though, you can take this picture, turn it on its side, lift it up, make a prism, and that'll also work. If you take this blue shape and shift it all around horizontally, it'll exactly cover up space. And also, if you do it in the vertical direction, too, it'll give you layers that cover everything up. And a little tiny calculation, this thing has surface area √6 plus √2 plus 2, which is 5.84, which is better than 6. And that's a picture of, 8 copies of this thing. For some reason, I tilted it on its side. And you like make infinitely many copies, you'll indeed exactly cover up space. So you can kind of tell that maybe there's a better idea, though, because here we sort of just took like a 2-dimensional solution and kind of in some boring way, extended it to 3 dimensions. So actually, me and Guy and Anoop Rao and Avi Wigderson, this guy is the greatest theoretical computer scientist of all time, by the way, Avi Wigderson. We came up with the following solution. I tried to plot it here. It kind of looks like, I don't know, an egg or something with 14 faces and some hexagons. And it tiles space. I'll show you a picture in a second. It has surface area like 5.6121. You can calculate it exactly. So that was a better solution. And somehow here's the picture. Again, I put 8 copies. I don't know if you can tell. It's like looking at it from a different angle. But you know, if you shift it all around, it'll cover up space, tile space. Now, actually, you can do a little better than this, because if you go back to this motivation with the foams, what you can do is imagine that this picture is actually made out of like soap film, and then you just like say, OK, physics, go, like do your thing. It'll like sort of slightly warp them, and they'll relax according to some ancient physicist, Plateau. He has some laws about how soap bubbles will interact with each other. And you can see if it'll, starting at this sort of configuration, will get you like into an even smaller shape. Of course, you cannot like actually do it in real life, so you simulate it on a computer. And you plug in this, and then it triangulates the thing, and like it gives you to this, which looks kind of similar, but I don't know if you can tell, like these edges are slightly curved, and like actually the face is like slightly wavy. It's not flat. And like it's changed shape a little bit. But anyway, it also works, and its surface area is a little bit smaller. It's like 5.6. And this is the best solution I know for 3 dimensions. But it's totally possible that you can get a better one, so you might try that in your spare time. So here's a picture of it with a ray tracer, and here's it filling up space in a similar way, and you know, just to show you that it looks like some foam. OK, so that was the story for the 3-dimensional version of the problem. Now, if you remember, at some point we were talking, not too long ago, we were talking about this unique games conjecture story. And we had this plan, me and Guy and Uri, to try to prove it. And for that, we didn't really care about what happens in 2 dimensions or 3 dimensions or 4 dimensions. We really would care about what happens in d dimensions, which is harder to visualize. So I showed you the 2 and 3-dimensional pictures first. Yeah, so we needed to understand this question. What can you say about the surface area of like the best shape in d dimensions that tiles space when you translate it by all integers? Well, let's try to think about the simplest possible thing. I mean, d dimensions is kind of complicated, but you can always use a cube. That's definitely going to work. And this surface area is 2d, because it has 2 times the dimension number of facets. Each one is a unit cube in one lower dimension, so 2 times d. And as for a lower bound, like something that you can't do better than, you see any tiling shape, you can easily show that it's going to have volume 1, because if it's going to fill up space by integer translations, like if it's less than 1, it doesn't have enough volume to fill up space. If it's more than 1, it'll have overlaps. So any volume 1 shape that tiles space has to have at least as much surface area as the volume 1 sphere, because you know, soap bubbles have like the least surface area for a given volume. It's called the isoparametric property. Now, I mean, a sphere actually doesn't work. Like if you try to tile space with spheres, like stack oranges, they don't work. But you can say that like it's not possible to do better than the surface area of the sphere, because any shape you come up with volume 1 has surface area at least that of the volume 1 sphere. Which, if you like look on Wikipedia or whatever, you can figure out what its surface area is. In d dimensions, it's about square root d. So this is what we really cared about. What is the least surface area, depending on the dimension, of a shape which tiles space in a cubical fashion? And we know that you could use this cube, so it's at most 2d. You could never do better than the surface area of the sphere, which is about root d. So it's somewhere between these 2 things. And this is what we needed to resolve. And in fact, we didn't even really have to solve this. In order for our glorious plan to work, all we needed was that the correct answer was not like the lower bound. It shouldn't be on the order of square root d. And not only did that seem true to us, we really believed that it would have to be like order of d. Like we thought like a cube has to basically be the best thing, because come on, like if you got to tile up space in a cubical pattern, like how could it like not basically look like a cube? Well, apparently it can. So it turns out that actually this A of D is like proportional to root D. There is some crazy shape in high dimensions that fills up space in a cubical pattern, but its surface area is like quite close to the surface area of a sphere. So I don't have any like visual picture of it, but it exists. In fact, we didn't even find it. We just showed that it exists. So that was a bummer. It meant our plan did not work, and we got nothing. Well, we did get to write a paper with the title Spherical Cubes. So that was a small consolation. So that was our plan. It didn't work, and in fact, nobody right now knows how to prove or disprove the unique games conjecture. OK, so that's kind of the end of my story, all my stories. I just want to say one more slide about theoretical computer science. We talked about MaxCut. It was pretty cool to me, and it's my favorite problem because it's the most basic algorithms problem in the whole world, I think. But to really understand its complexity, and we're not even really done understanding its complexity, we took a look into geometry, into probabilistic proofs, and the nature of proof, voting theory, and the mathematics of social choice, foams. I mean, all sorts of crazy, amazing math properties. And this is what I really love about theoretical computer science. Not only can you study whatever you want, because everything in a way is connected to computation and information, but even if you fix one computer science problem you want to study, like MaxCut, you get some just really amazing, beautiful interconnections with all different parts of mathematics and all different parts of science even. OK, that's it. Good luck on the final.